Scientific notation is a system for expressing very large and very small numbers with less symbols. First, I'll go over the steps of converting a decimal to conventional scientific notation. Our first task is usually to move the decimal from where it is to a new location. But what is the conventional location to move it to? The convention is to put the decimal in a position where there will be one and only one non-zero digit to the left of that decimal. So in the example 40, the convention will be to move the decimal over one place so that there's one and only one non-zero digit to the left of it. Now we want to write down that new number with the decimal moved to the conventional position. Let's do it for the others here too. 600 will become 6.00. Notice that the decimal point is expressed here, which means that these two digits are significant figures, and that's why I kept them when I rewrote the decimal as well. This one will be 9. And here, I don't have to keep the zeros because these are not significant zeros, because no decimal point was expressed. For 123, I'll have 1.23. And for this, we'll make it 4.0. So that's step one. We also want to determine the number of places that the decimal had moved in each case. So for this one, notice that I had moved the decimal over just one place. So let's write that down. In the case of 600, I'm moving it 2 places. And this number is going to become important later. In the case of 9 million, the decimal point is not visible, but it is at the end of the number. It's assumed to be there. So let's count 6 decimal places. For 123, we're moving it 2 places. And for this one, we're actually going to move it to the right instead of to the left there, but that is 3 places. Now, we can't actually leave our final answers like this, of course. 40 is not equivalent to 4. If you owed $40 to a person, you couldn't give them $4 and have them be satisfied, right? So we have to make a modification to the number in order to make these two things equivalent. What we'll do is we'll add times 10 to a power. And in a moment, we'll determine what the power should be for each of these cases. All right, it says here the number of places the decimal moved is going to be the magnitude of the exponent. So here, since we moved the decimal 1 place, I'm going to put a 1 here. We moved this decimal 2 places, so I want to put a 2 there. Here was a big move, 6 places, so we're going to put times 10 to the 6. This one moved 2 places. And this one had moved 3. However, that brings us to the very last thing that we have to consider when doing this. We do have to examine the balance between the old and the new expressions to determine what sign the exponent should take. So if I just put a 3 here, for example, that actually wouldn't be quite right. See, 0.004 is a very small number. But 4 times 10 to the third would actually be huge. That would be 4,000. Okay, so 4,000 is definitely not equivalent to 0.004. For that reason, this exponent needs to be a negative. Now, what do I mean by examine the balance? Like, how does that help you determine what the correct sign of the exponent should be? Well, if you take this example, 2,000, currently the decimal is at the end. We want to move that decimal to the conventional position. So let's write out an equation here. 2,000 equals 2 times 10 to a power. You could think about 2,000 as 2,000 times 1. So if we compare the new number to the old, we see that 2,000 is much bigger than 2. So the number part of this decreased. That means that the 10 to a power needs to be bigger than 1 in order to compensate for that change. So that tells us that our exponent needs to be positive. Why? Because 10 to the 0 is 1, and we need a number that's bigger than 1 in that place. So we're going to put a positive 3 there for the exponent. Now, why is it 3? Because the decimal moved 3 places. So anytime we move our decimal in the number to the left, we'll compensate with a power of 10 that's positive. And then that'll be our final answer. 2 times 10 to the third.